All right. So, how are you guys doing? That good, huh? Yeah, I'm feeling kind of shitty. Gave you guys the day off. You let me down. I'm kidding. I'm not blaming him. Anyway, so we'll do science because science isn't political. So today, what am I doing? First thing I'm going to do is go over your midterms, which I have graded. It takes me forever to get the homeworks done, but the midterms I can get done pretty good. Jonathan's out, Nicole's out, Eli is here. You guys can start sitting in alphabetical order. Justin's John.
Choose to do that.
Oh, yeah.
No,
Okay.
I'm just reading.
All right. Some of my notes might be cryptic because I was trying to do it in a hurry because I wanted to finish. And yours I did not print. I just gave you a sheet of notes.
Sounds good. Thank you.
Anna. There we go. So everybody did pretty good. I'm pretty happy with how everybody did. Yeah, I mean, at the surface, you know, it's a challenging midterm because I don't really give you anything. I just say, start with nothing and derive sound waves and tell me how big stars can get. So aesthetically, it's, you know, it's non-trivial, but you guys, I think, did a great job. Mostly because those are the things that I made sure I worked on, but there you go. Okay, so let's first, real quick, go over the test. I'm not going to spend a ton of time on it. Mostly, I'm just going to drive by each one of the problems and highlight some common mistakes. Just because if more than one person made a mistake, then you might have learned it together. And you know, maybe that's not something that I clarified very well. So, okay. So the first one was derive. What's that? One is derive continuity, assuming mass conservation. And several of you had said that dm dt equals 0, and therefore d rho dt equals 0, but that is not a true statement. You can't say that. It was intriguing how people got to the actual solution from this, but this isn't accurate because you wind up getting an extra term that you have to magic away somehow. The way to talk about it is by saying partial of m with respect to t. Why is it partial? Because we're holding everything but the mass fixed. So I have some surface, and inside that surface, mass is fixed, but the surface is fixed. And the mass inside is going to change, but it can only change by the flux, which is rho times v dot dA. So this is the bit that you have to argue with words or somehow. Oops, sorry. I don't need to do that. I didn't really go into detail why this is the flux. Let's talk about that for a second. So if you just have a surface, and I want to know how much, and I've got some quantity Q that's flowing across this surface, and I want to know how much Q has flown out of the surface. Let's say I've got some can, some cylindrical test surface. I want to know how much material is in this surface after a time delta t. Then that's going to be the area of the can times Q per volume times the velocity times delta T. The velocity times delta T gets you this length, and the area gets you the surface. So area times V delta T gets you the volume, and Q per V is what you've got on the inside of this. So this winds up just looking just like, so this is after a time delta T, so if we want a rate, then we just divide by delta T. And we get that the rate of mass loss is going to be rho V times the area. So this is why this is the flux across the surface. So this is the stuff that flows across the surface. And it's negative just because of the convention that the normal is outwards. And if the flow is going down, if the mass is going down, then the flow has to be outwards, which means you need a minus sign because the flow has to be going in that direction. So if the flow is the same sign as out, then dm dt needs to be negative, so we have to pose a minus sign. Then we do Gauss's law, and this says div rho v dv, and then you can pull everything into one integral over dv. This turns into an integral over dv, and you get d rho dt plus div rho v equals 0. But starting with d rho dt equals 0 is not the way to start. That's not a correct statement, because d rho dt, the convective derivative, is equal to rho div v, not 0. So I don't take a ton of points off for things like that. So here, stop me. I'm just going to kind of go through it. If you've got questions, especially if you've got questions about my notes that I left, holler. But I'm just going to kind of quick go through this, because the rest of the day we're going to start MHD. So I've got a bunch that I want to get through. Okay, second, beginning with x equals ma derive Euler's equation. This is relatively straightforward. There's a couple of different paths up the mountain, but I think everybody, I don't think I took off any points for this one. I think everybody said meaningful enough stuff. So you need to start with dv dt, which turns into the convective derivative, d partial v partial t plus v dot grad v, however you got here. And you need to get, the pressure is grad p, 1 over rho, because we're doing everything per unit mass. Some combination of those things needed to be on your paper, and I think everybody got it. So, blah, blah, blah. Yeah.
On my test, like where I say that dv dt is equal to the convective derivative, you wrote like y. Like what kind of answer would you have?
Chain rule is what I'm looking for there. So I didn't take any points off for that, I don't think. I just wanted you to think about how are those things connected. So it's just chain rule. It's not very complicated. But 3, linearize and combine Euler and continuity to make a wave equation for density. I'm very pleased with you guys. Like, everybody did a pretty good job and had something at least sensible to say. Not everybody did all of it, because this is a more complicated problem, so there's several places to miss a couple points. I decided a while ago that on tests, every question was going to be worth 5 points, because that way I don't pile up all the points onto a hard problem that people are going to mess up. So it's a way of kind of evening the playing field. So the easier questions are also weighted nicely. Okay, so the basic idea, and not everybody got everything on this, but so you start off with d rho dt plus div rho v equals 0, and dv dt plus v dot grad v equals -1 over rho grad p. Okay, so one thing you need to do, and there's several orders that you can do this in, and a couple of you went all the way and got a dispersion relation, which is not what I was asking. I was just asking for the wave equation. Mostly because what I want to do is the whole process, but if you trip somewhere in the middle of that derivation, then the end of it gets really bad. So if you went all the way through, that's great. A couple of you got the right dispersion relation through a correct means, but jumped past ever writing down a wave equation, which is also a legitimate way to solve the problem. Not exactly what I was asking for, but that's all right. I like the answer. So one thing you need to do is get rid of P. So you say that grad P equals dP d rho grad rho. Here I'm making a very important assumption that the displacements are adiabatic. That is why I can say that this is true, and not also dP dt grad T. So if I was just doing chain rule, I would need a second term. But because I've assumed that it's adiabatic, it only depends on pressure, which is kind of the magic of how this works. And then we call this C squared grad P, grad rho. I would plug that into there, so this becomes C squared grad rho. And then you need to linearize, and there's several little pitfalls that people made, but nothing really major. I think everybody basically did this right. You wind up with rho 1, rho naught v1. v1, this term goes away. This is a rho naught, and this is a rho 1. And you're left with this equation. Once you've done this a bunch of times, you can just do that. Like when you're linearizing things, you can just look at the equation and be like, that's going away, that's going away, this is my constant, this is my thing. So because you've done it a bunch of times, not because of wizardry. So you get these pair of equations, which are now my linearized equations. Let me highlight this. So this is a 1. This is my background solution. This is my perturbed velocity. Here's my perturbed velocity. This goes away because nonlinear. Here's my background velocity. Here's my perturbed density. So in both equations, I have one perturbed density and one perturbed velocity. Now you've got to remember the stunt to combine these into one equation. And the stunt is pick the variable you want. We want rho, so we're going to get rid of v. So I need to make these two terms look the same. So that means I need a dt on this one and a grad on this one. So I take a d by dt of this whole equation and a grad of this whole equation. And then I add or subtract. Add. Or you can say I'm solving for this term because this term turns into this term, and just plug in, and that works fine too. And you're left with the wave equation, which is where I wanted you to stop. The second derivative of time, of rho with respect to time, minus c squared d rho dx to equals 0. So this is a wave equation for a wave that propagates in time and space with velocity c. And that's where I wanted you to stop. Yes, most everybody got everywhere. If you forgot how to cross-differentiate, that's okay. That's why I stopped at the wave equation. If you said everything else right, you got a lot of points. And then the next one, I'm pleased with how this midterm comes out because it asks all the questions that I want to ask. Like, this is what I want. I want you to start with nothing and get to turbulence. Okay, in deriving gene stability, we find a modified wave equation. That looks like d squared rho dt squared minus c squared d squared rho dx squared equals 4 pi g rho naught rho. These are different. This is rho. This is my fluctuating rho. So the first question is find the dispersion relation, which I think everybody nailed. So here you just take e to the I k x minus omega t. And you drop it in, and you're left with omega squared minus c squared k squared equals 4 pi g rho naught. And everything else cancels out. So now the second question people had a little trouble with was find the most unstable, find the biggest, the largest unstable wave number. So how do I find what wave number is going to make my system unstable from the dispersion relation? I know a lot of you got it.
Whatever's imaginary.
Yeah, so you solve for omega, and you look for when omega is imaginary. So you just shove that over to the other side, and we're left with omega squared equals 4 pi g rho naught rho minus c squared k squared. And we need to know when when the interior is less than 0, and you're left with my cheap ass brain. Oh man, he didn't do it right. I should write down the solutions. What is the Jeans wave number? Hey, there you go. 4 pi g rho naught. So you get the k is 4 pi g rho naught over c squared, square root of all of that. So this is the biggest unstable wave number. So if k is smaller than that, then this is a smaller number and less likely to be to give you an imaginary omega. So what does this k represent? It's the biggest wave number. How do I get a Jeans length out of this? How do I get a length? What's the relationship between length and wave number? 1 over. Really 2 pi over. So lambda is 2 pi over k. And then we get a Jeans mass by saying 4/3 4 pi over 3, which is really just 4, times the length cubed times the density. And if that's really all you wrote, that's fine, as long as there was some connection to what the Jeans length was. And then what does this represent? Somebody.
Jeans,
What's that?
Jeans math.
It's the Jeans mass. And what does it mean? If I have a cloud of gas with some density rho naught, what is the Jeans mass for that cloud?
It's the limit before it collapses.
That's right. So a perturbation has to be smaller than this or it will collapse. So this is, you can think about this as the typical fragmentation size for a molecular cloud. So if I have a cloud, this is the typical size of things that it's going to break into. Formally, it is the most unstable wave number, but then we wave our hands because clouds aren't really nice, uniform, linear things like this. Boom, boom, boom. Does anybody have any questions about that one? Feel pretty good? And then the last one, okay, so for the last one, I feel like the way I wrote the question made sense, even though it feels kind of convoluted. So I had written down Navier-Stokes, and I had written down dV dt plus 1 over rho grad P equals minus V dot grad V plus the force plus nu del squared V. And I asked you to tell me what each one of these terms does in a turbulent environment. So I was looking for, I think most everybody did a pretty good job on this. Well, no, let me rephrase that. Everybody did a pretty good job of this. Some of you really killed it. Really did a great job. Oh, actually, I need the actual questions. Why am I closing that up? Yeah, so it's kind of an open-ended question. So I was pretty generous with results. Mostly, I was looking for. Let's do it as a function of L. So this is K. If you're going to draw the same function for L, it's going to look just backwards on the axis. Some of you had done some weird things when going from K to L. So we start off at the large scale, and this scale is set by whatever scale the force is acting at. So the force is providing the large scale, and the nature of the force is defining what large scale means for our system. So if I have one of those little battery-powered milk frothers, then the length scale is, 1 centimeter at the bottom of the milk frother. If I have, Hurricane Irene, that's, you know, 1,000 miles across, so the length scale is 1,000 miles. But then it's, you know, that's a lot more complicated because there's no coherent motion on that kind of size scale. So the length scale, it's kind of vague, but it's set by what the forcing is doing. So this defines, the forcing defines the outer bound. Then in the inertial range, the nonlinear term, energy is conserved in here, and the nonlinear term is what shreds vortices from one size scale to the next size scale down. And that continues down until you get to the third term, which is the dissipation term, and down here, molecular diffusion, and whatever else actually happens. We don't 100% know how that gets dissipated, but it gets dissipated somehow down at the bottom scale. So I was really looking for you to say something basic about the three things and the three regimes of turbulence. Yeah?
I have a question about this. So like the large scale depends on F, and that, like, you know, is dependent on what's the external force. But
Yeah.
is the small scale, like where the diffusion happens, is that always like at the same or similar point for whatever diffusion is happening?
That's a great question, and the answer is no, and the reason is magic. And let me explain, because that's a cryptic answer. So let me tell you how turbulence decays, and this will start to make your question make more sense. So say I stir up a pool with a huge paddle, and my whole pool is turbulent. This is my outer scale, and this is my dissipation scale. So I start off at t equals 0 with a fully developed turbulent pool. And then I stop stirring it, and I let that turbulence decay. So what happens is this energy goes down this way. So from the top, I'll see my large scale decreasing like that. The inertial range stays the same because the inertial range can't tell that you stopped the forcing yet because it hasn't gotten there. Have you ever watched someone drop a slinky, like holding a slinky and drop it from the top? So if you take a slinky and you hold it so that it's long and then let go, the bottom doesn't start moving. You can watch the compression wave. Let me do this all on my camera. You can watch the compression wave go down, and the bottom just stays there floating magically until the compression wave gets to it, and then it falls. Watching slow-mo videos of this blows my mind, even though I fully understand that that bottom part is still experiencing every force that it was before, and it's not until the knowledge of the force changing gets to it that it collapses. So this is something kind of similar. So in the inertial range, nothing really changes as the turbulence is decaying. But what's happening at the smaller range? So the Reynolds number, so what we found was that the dissipation length is the outer length times the Reynolds number to the -3/4. So what does this say if the outer scale is decaying? This means that Reynolds number is getting smaller, so the dissipation length gets bigger. And this is the thing that you actually notice if you're watching a film of this. In GFDI, in the basement of Keene, there is a bottle of this fluid that shows this very, very coolly. I need to see if I can dig it up and get them to lend it to me. Because it's really, you can watch it happen. As you watch the turbulence decay, you can see that all the small stuff stops first. So once you're not dumping energy into this scale, then those structures disappear. And then you're left with, so the tiny structures are gone, and you're left with these slightly bigger structures. So the dissipation scale increases upwards as the Reynolds number decreases. Or put another way, the dissipation scale depends on how much energy I'm putting in the large scale, and it kind of just figures it out. Like nature just kind of figures out what scale to set the dissipation structures at so that I'm dissipating all of this energy. Does that make sense? So it's kind of wild. Why does the tiny stuff know what I'm doing at the outer scale? Well, because it's all connected, and you're dumping this energy in here, and it dumps down until it can't anymore, and then it makes little structures. We don't really understand the structures. We know that they're fractal. We know that there's not a single size scale. It's a fractal size scale. There's a hierarchy of different size scales. So there are some big ones and some little ones kind of throughout this region, and it's very complicated. So it's pretty interesting. Okay, any other questions on turbulence or anything yet?
So, and you were saying the milk frother and hurricane analogy?
Yeah.
But, like, when you use a milk frother, there's like, the boundary's really close to where you're making milk frother.
That's true.
So is that, like, would it act more like a hurricane if, like, is it about, like, absolute length or, like, relative to?
A little of column A, a little column B.
Okay.
So when you're close to the boundary, then a lot of this kind of breaks down, and you have to deal with the turbulent boundary layer. Because in that scenario, you're not wrong. You're stirring everything in one direction. So if you're careful, everything will spin up to that rate. So we're kind of assuming that you've got a bathtub full of milk that you're trying to froth, and the boundary's far away. So because the boundary condition makes everything a lot more complicated.
Right.
So that's for a different class.
Okay.
Or research topics, like those are research engineering topics. Yeah.
So can you do the physics of, like, if I have a little cup and I'm frothing it, and, like, you know, there's a certain height you want the frother at, so that the, like, milk, all the milk is churning in, like, some cylindrical way. I don't know if you froth milk that often, but
More often than you'd think.
but you know what I mean. You have to do it at that right level so that you're, you know, getting like those micro bubbles, but then you also want to see the whole milk thing turning. Is there a way to, like, given the boundary conditions, could you calculate, like, exactly where you want that, how big you want your frother? Or is that like a super hard problem?
No. Well, so what I think you need is so the frother works because it's entraining air into the flow. So you've got your milk, and you got the height of your milk, and you've got your milk frother, and it's going to make a little cone where the centrifugal force makes a little wall, and that will then fall back down on itself. So as long as the typical length scale of whatever turbulence you're generating from the mixer, as long as that is close to the top, then you'll entrain milk. I suspect that if you carefully sort out, so like some things you can just solve. Like if I have a tank, a round tank, and a hole in the bottom, and I spin it ever so slightly, it'll make a tornado, and you can compute exactly the wall of the tornado. So I would start doing something like that by saying I'm going to make some kind of tornado. What's that wall going to look like? How tall is it going to be? So yeah, that's an interesting question. I don't actually know how to solve it, but I can make some stuff up.
I feel like for something like this, there's only so much that you can do with just the frother, which is why we come to blenders where it's at the bottom.
Yeah.
And then there is the ridges on the side, so it makes everything be more turbulent on the inside.
Right.
I think that's because if it was just smooth, then it would just be going around and not mixing.
Mm-hmm.
But because the blenders have those ridges on the inside wall,
Right.
as it rotates, it
Makes a slipstream and,
Yeah.
and makes it turbulent. That's right. Okay, so now, that is it for the midterm. I was going to go over your readings, but I had just technological problem after technological problem with getting to the reading this morning. Mostly the internet was not working. And then the internet started working in my office, but I didn't have my phone because it was in the car. So I go out to my car and I get my phone and I come back here and I think, oh, I'm just going to sit here and go through the reading questions. But the internet is down. So anyway, I haven't gotten to your reading questions, and I gotta put that is just gonna be distracting me. That's gonna go away. My poker buddies are having political conversations on my phone.
I'm sure they are.
And one of my buddies covers the Capitol for the university. So he's a reporter, so he's like in the thick of it. So anyway, so today now, I am talking about Oh, thank God. MHD. So we're gonna, let's see, we're gonna go over here. That's a bummer. We're gonna go over here, talk about the things we're gonna talk about. So we're going to first start talking about Maxwell's equations, and I'm going to talk about the two unit systems. The one that you use for E&M, which is a stupid unit system, or CGS, which is not a stupid unit system. But CGS is not the one that won the fight, so now I'm a weirdo for using CGS. Second, we're going to introduce plasma. And we're going to talk about length scales, and we're going to talk about time scales. We're going to talk about the Debye length. We're going to talk about the cyclotron frequency. We're going to talk about the plasma frequency. And then I'm going to show you how to do fluids with a magnetic field. So then we're going to combine, so we're going to get a force, and we'll get an induction equation. And I think I have plenty of time to do all those things. Okay. So how many of you take an E&M? Most of you take an E&M. Okay, cool. I am going to assume that you haven't, because that's how I always do this. But since you've seen Maxwell's equations already, this won't be super surprising. So let's start with SI. Div B equals 0. So this says that if I take a little closed surface, all the magnetic field lines that come into it have to go out of it again. So a magnetic field line, which is a fictitious object, there is no real thing as a magnetic field line, it's a vector field. But to the extent that talking about vector fields as lines makes any sense, magnetic field lines don't end anywhere. There's no edges. They always make loops. If E equals 1 over epsilon naught rho free. This says that electric fields end on charges, and the magnitude of the electric field is caused by the magnitude of the concentration of charges. So you have del cross B, which equals mu naught J plus epsilon naught d E dt. I'm going to need to write that a little smaller when I get to the other side. And this one's harder to really get a good interpretation of because it's really about the geometric structures. So curl of B is about the spatial structure of the magnetic field. And that gives rise to currents. So if I have any kind of curl in the magnetic field, that's going to drive a current. Oppositely, if I drive a current, I get a magnetic field. That magnetic field has a curl. Plus some time-changing magnetic field. And these two guys are related like E and J, but by whose law relates electric field and current?
Electric field.
Yeah. You probably, you know this law.
Biot-Savart?
No. You know this law from circuits?
Ohm's law?
It's Ohm's law. because my electric field turns into my voltage, and current is just current. So electric field and current are also related by the resistivity, just like Ohm's law that you learned when you did circuits. You have to treat what the resistivity is, because now we can derive what the resistivity is going to be based on how particles bang into each other. I'm not going that deep down that rabbit hole yet. I will probably do that on Tuesday. So structures in the magnetic field give you currents and time-changing electric fields, and also curl of E equals minus dB dt. So this is the way you have learned them. And one of the cool things you can do about this, with this, is you can take these two equations. Let's take these two equations real quick. I got, and let's get rid of the free currents. So we just have that. Let me say before I do that. Why are they in this form? I've got a div of B and a curl of B. I've got a div of E and a curl of E. This is enough to completely describe E and B. So it's a cool theorem. It's Helmholtz's, do I have it or no? It's a Helmholtz's theorem that if you have the divergence and the curl of a vector field, that is equivalent to having the whole vector field. Now, solving it is maybe a headache, but you have enough information to solve it. In theory, you can solve for the full thing. So this tells you about not just the magnetic field and electric fields, but how their derivatives behave. So let's see what we can do with this. So I have curl of E equals minus dB dt, and I have curl of B equals mu naught epsilon naught dE dt. Anybody see where I'm going to go with this? So I'm going to get rid of, let's get an equation for B. So I've got this d by dt and a curl E. So let's take a time derivative of this one and the curl of this one and add them together. And I'm going to skip some vector identity. So I've got the curl of a curl, which turns into del squared. So the curl of the curl is div B, no, grad div B, that's not a vector, minus del squared B, and that's 0 because of Maxwell 1. And then the other side, you get mu naught epsilon naught dt squared of B. So you can write, I dropped a minus sign somewhere. I got a minus sign on this one, and there's a minus sign on this one. So you're left with del squared B minus mu naught epsilon naught, dB dt squared minus mu naught epsilon naught dB dx squared equals 0. What kind of equation is this? This is a wave equation. What kind of waves is this describing now? What do we? What's that? EM waves. What do we call an EM wave? Light. So mu naught epsilon naught is c. C squared. Right? What's that?
I was just saying the fact that we haven't even done this in E&M. It's kind of crazy.
Oh, really? That's okay. You don't need to
Yeah.
do it in E&M.
No, but this would be nice, I think.
Yeah.
It's pretty neat, right?
Yeah.
This is where photons come from, and this is where they realized that. What's that?
No, we have seen this.
That's possible.
Oh, I just knew that.
Oh,
Yeah,
okay.
no, I just did that with the GRE, that's why I remember.
Oh, okay. Yeah, it's a nice. It's a beautiful little proof, right? So mu naught and epsilon naught add up to be c squared. So now we're going to roll back 50 years. So I think I told you about this. So one of the most interesting cab rides I've ever taken was with Gene Parker. And Gene Parker, this book is dedicated to Gene Parker. He's Jesus Christ of plasma physics. Like, he brought plasma physics, like Moses, he brought plasma physics down from the mountains for us. He's the only person, he passed away a year or two ago, but he was the only person that NASA has ever named a satellite after while they were still alive. Because they named the Parker Solar Probe after him because they were going to shoot this at the sun and try to test a whole buttload of his theories. So anyway, what he got talking about was the development of SI and why SI sucks. Because what have I done here? So what is the result of this? Now we've introduced a new quantity, a new unit, the ampere. This is a new fundamental quantity, and we have mu naught, which is a new fundamental unit that we have to measure. So now we have a thing to define and a quantity to measure. But it's entirely unnecessary. You don't need that at all. Let's look at the CGS formulation. And really, I'm just motivating why we're going to use CGS for the book, because that's what we do. Most plasma physicists use CGS. Most astrophysicists use CGS. Engineers use SI. So since I'm an astronomer, let's go through that. So in CGS, div B is the same. And let me tell you, I spent most of my graduate career trying to keep div B 0 in a code, and I hate this equation so much. But it's so important. Div E equals 4 pi times rho free. No more epsilon naught. You don't need that. All of our knowledge of the permittivity of free space, we can just load into the definition of the charge, which we'll get to. Curl B equals 1 over C times 4 pi J plus dE dt. Now there's just a C here. And this is an actual fundamental constant. Mu naught is a made-up constant. C is an actual fundamental constant. Now you can see, if I'm going to do this equation, if I'm going to do this derivation the same, I'm just going to have C squared here. Because you wind up with a C squared there. And I'm left with the wave equation just saying that's travels with the speed of light. And then del cross E equals minus 1 over C dB dt. So now in the CGS formulation, the Gaussian formulation, this is the Gaussian formulation. There are several ways to do this. You'll hear this called Gaussian as well. So I got a C here and a C here, which is where the C squared comes from. But now what else can you see from this? You also see that E and B have the same units. So this is E over distance, and this is B over time, and this is 1 over distance over time. So E and B have the same units, which when you get to the end of E&M2, you'll get to relativistic E&M. And there you'll learn that the electric and magnetic field are not different things. You can roll one of them into the other one by going fast enough. So if I have an electric field and I'm going fast enough, really fast, it becomes a magnetic field. That should be natural, right? There's one tensor that describes the electric and magnetic fields at the same time. Should be the same thing. So this is the way we'll formulate Maxwell's equations for everything that we're doing. And the big differences are, there's not a mu naught, there's a 1 over C. You pick up a 4 pi for the J. The 4 pi is geometry. This 4 pi is geometry. This is just for Gauss's law, right? This just makes Gauss's law make more sense, because you always get, like, if you've got a point charge, you got to use 4 pi times the delta function to make everything make sense. And I get a 1 over C here, whereas there's no units here. So here, from this equation, you can see that E and B are different in units by something that looks like a velocity. There's no extra field. There's no new field. There's no new constants to measure. So it's a more fundamentally true set of theories. Oh, the other thing I want to point out is the force law, because I'm going to need them. So what's the force between 2 point charges? So in white chalk, in SI, the force between 2 particles is 1 over 4 pi epsilon naught Q1 Q2 over R squared. In CGS, the force is just Q1 Q2 over R squared. And whatever unknown constant you want to put there is just absorbed in this other unknown constant that's the charge of the electron, which is a thing you had to measure anyway. So we just pack all our ignorance into one thing instead of splitting it across multiple things. And the force law in MKS, force between 2 line charges is mu naught over 4 pi I1 I2 over R. Whereas in CGS, its force per length is 1 over c squared I1 I2 over R. And I don't have any fundamental constants that I need to measure. And I don't really have a unit that I need to define either. Because now you can see the stag coulomb, or the ESU, is the unit in CGS. And you can tell what the units are. So I get a dyne. A dyne is the unit of force in CGS. It's a centigram, it's a centimeter, it's a gram centimeter per second squared. And it's equal to ESU squared over centimeters squared. So an ESU is simply equal to the square root of a dyne centimeter. So, okay, units that have square roots in them make my brain hurt, but that's on me. So it's a more fundamental way to deal with things. So physicists like it. It's not as easy to do maybe calculations with, so engineers don't like it as much. Because a gram is a really dumb unit. An erg is a really dumb unit if you're going to measure anything real. An erg is the energy of an ant doing a push-up. It's a centimeter. It's a gram centimeter per centimeter squared per second squared. So an ant is like a centimeter, right? So an ant running around. That's an erg. So anyway, there are some ups and downs. I'm not saying that this is the most perfect system, but there are fundamental reasons why we use it as astronomers and plasma physicists. So I'm going to leave that up there, and then I'm going to talk about plasma. So we have been dealing with, I'm going to leave all of those up there for the remainder. And if you, I want everyone to be familiar with Maxwell's equations in Gaussian units, but I'm not going to ask you to solve any problems starting from these. So every problem we start is going to start from the MHD equations, because formally I don't assume that anybody's had E&M when I teach this class. And that, I think we're going to change things, so maybe I can change that, which might mean that there's more plasma in this going forward. But presently, we're just going to talk about it in the general sense. So I have a cloud of gas, and it has electrons, which are negative, and it has ions, which are positive. So the ions can be hydrogen. So what's a hydrogen ion? It's just a proton. Or it could be something big, if you have a big cloud of molecular gas in outer space, the ions are typically charged molecules. So you get molecules like HCNO and H2NO plus, and CN. There's a lot of cyanide in outer space, just kind of floating around in big clouds. That can get charged. So it's typically in outer space, it's big molecules that get charged, but it's whatever thing is your donor. And typically, these wind up being bigger atoms. Why? Is it easier to take an electron off a hydrogen atom or an oxygen atom?
Oh, huge atom.
Big atom, because that big potential is screened out by the rest of the thing. So the last electron on an oxygen atom is pretty easy to take off. The last electron on a hydrogen atom is also relatively easy to take off. But we wind up having bigger molecules that are charged, or bigger atoms that are charged. So we'll have some electron density and some ion density. And next week, I'll show you what the evolution equation for the electrons and the ions should look like. And it looks, like Navier-Stokes plus extra term plus extra term plus extra term. So there's, so when I write down the equation for we'll also have an electron velocity and an ion velocity. So we have, for everything that we did before, we have a density, and we have a velocity, and we have a pressure. You get an electron pressure and an ion pressure. So the electrons have pressure between themselves, and that just looks like isotropic pressure. And the ions have pressure between themselves, and that just looks like an isotropic pressure, just like a pressure. And those pressures are separate. And then also you have an interaction term that is scattering off of electrons and ions, so they can bounce off each other. I'll go through this in detail next time, but I just want to set the stage. So I've got this cloud, and it's got, and it might have a bunch of neutrals, so we don't have to have the whole gas fully ionized. If it's fully ionized, then you can say one thing, but if it's partially ionized, then you have other things to say here.
I was gonna ask, what's keeping these charges from, what's keeping those positive ions from taking in these electrons?
Yeah, it's a good question. It depends on the system, but typically it's temperature. So they call plasma the fourth state of matter, right? So you start with ice, that's a solid. You dump in energy and you break all those solid bonds, and then you get a liquid, and that's at a higher temperature and a higher state. And then you dump in more energy and you break those liquid bonds, and you get a gas. You dump in more energy and you start to take electrons off of the water molecules, and then you have a plasma. So mostly it's the kinetic temperature of the gas that keeps it ionized. But you can also do it with X-rays. You can do it with charged particles. If you have a beam of protons, that'll also make a plasma. Yeah.
So why does microwaving a great big plasma?
Because those great big, so that's a fun thing. I don't have, if you could email me that, I will pull up something more detailed than the BS that I'm just gonna spit out right now. Because that's an interesting question, and there's interesting physics. So what happens if you haven't done this before, you take a grape and you cut it in half, but you leave just like a tendril of skin connecting the two halves, and then you put it in the microwave, and then sparks will jump from one side to the other. And so what you're doing is the microwave is kicking off electrons from the sugar molecules. So the sugar molecules are large hydrocarbons, and they have a lot of kind of loosely bound electrons. So once you start freeing those electrons, then you have a bunch of electrons kicking around, and then they arc. So, and because they start to arc, then you get a plasma. So you get charge separation, which is actually some kind of plasma, but then when it arcs, then you can see that it's a plasma, because you can see it breaking down the air. Yeah.
So an arc is the same thing as a plasma?
Arcing and plasma are related. You can have a plasma that isn't arcing. So this is like a thundercloud. Think about a thunderhead. You'll have a charge separation, which is kind of a low-grade plasma. And then the lightning bolt is the arc, and that also makes a lot of plasma. So the lightning bolt makes a lot of plasma along its route. But you already have this very, very weakly ionized plasma in the cloud itself. So now the ionization of the cloud is so weak that I don't think you'll have any plasma effects. I don't think, but that's an interesting question. I don't actually know, because I'm not an expert on that. But the arcing makes more plasma as it goes. So yeah, you can make plasma at home. You can Mark, the demo guy. He's wonderful. He's got all these great demos and knows so much about them. He has this microwave, And in the microwave, he has a little beaker full of carbon dust that he got from burning a piece of cork. It's just carbon ash. And he puts that in the microwave, and it is amazing. It's an incredible light show. It's just sparks everywhere, and it just glows. It's amazing. Yeah.
Can we have a class field trip to Mars?
That might be fun.
Right?
There have been a number of great demos that have come up. I think that would be pretty fun. Actually, that's what the open house is for.
Oh, is that actually happening in the
Yeah.
spring? Okay.
April 5th.
Okay.
If
But
you
I
got-
want a private tour.
That's what going and doing the pre-sessions are for.
That's
so
true, that's true.
Sit down
So
with
volunteer.
Yeah, so everybody should volunteer for the physics open house because it's really a lot of fun. Like you just do physics demos for little kids all day.
You
and
said it's May 5th?
April 5th.
April 5th, okay.
I'm like 98% sure about April 5th. Okay, so one of the things that, okay, cool, good, I got time. So I have 3 things that I want to talk about. So what we're going to do is we're going to take Maxwell's equations and we're going to get rid of the electric field. Why? Because I can, and it is the appropriate thing to do in a lot of scenarios. Also, getting rid of a variable makes everybody's life so much easier. So we'll get rid of the electric field, but first we have to justify why we can get rid of the electric field. And there's 3 things that we're going to look at. We're going to look at the Debye length, we're going to look at the cyclotron frequency, and we'll look at the plasma frequency. And the plasma frequency is the more important of these 2 frequencies. But if you can't derive the cyclotron frequency off the top of your head, I want to show you how to do that because that's a real valuable thing to know how to do. Because it's easy and easy. Okay. I try to never use the word easy because it's not. Like you have to have built up everything that you've already built up before you get here. But now once you're here, it's straightforward. So let's talk about these 3 length scales. So basically, electrons don't have any mass relative to the ion, right? So I mean, the electron is 1,000th of the proton mass. So when I have an oxygen atom, it's 18,000 or 16,000 times bigger than the electron, right? So it's your ions are tens of thousands of times larger than the electron. See, the electron is basically just moves around for free, right? You put a little bit of force on it and it just goes. So what we need to do is make sure that we're larger. So if we're so the systems that the constraints that we're going to impose on being able to get rid of the electric field is that we're larger than the Debye length and longer than 1 over the plasma frequency. So the time scale has to be longer than whatever the time scale for the plasma to respond. And we have to be larger than the screening length. So let's talk about these 2 things. So the first thing is the Debye length. And the basic idea is if I take a proton and I put it in my plasma, I've just got all of these free pluses and minuses floating around. What's going to happen? I just take one charge and I stick it here. What's going to happen? What's going to happen to the minus charges?
Move towards it.
They're gonna move towards it. And what's going to happen to the positive charges? It's hard to draw a lot of those. They'll make like a sandwich. Okay, it's not going to be a sandwich quite like that, but I have my big positive charge. I stick it in my plasma. Electrons will move towards it because it's positive, and then protons will move towards that. And then after a certain distance, this distance that we're going to call the Debye length, you can ignore this thing. It's screened out by the plasma itself. Does that make sense? So I'll define what the Debye length is in a second. I'll derive it. But the basic idea is whenever I set up some kind of charge disturbance, the electrons move really fast to try to neutralize that charge disturbance. Nature hates things being out of whack. It hates being away from equilibrium. So it tries to get towards equilibrium, and this Debye screening is one of the ways that it does that. So as long as the structures that we're working with are larger than the Debye length, then we can ignore the electric fields. So these all make electric fields in here. As long as we're bigger than that, then we don't really need to worry about what the electric fields are doing, because on scales larger than the Debye length, the electric field has all canceled itself out. If you look real close, you'll see lots of complicated electric fields, and you'll have to worry about them. But oftentimes, this is a pretty small quantity. This is a few angstroms, so it's not really very large. Unless you're in outer space, in which case it's a few solar radii, but that's still not very much. Oh, that's a good homework problem. Compute the Debye length for stuff. I don't think I have you doing that right now. I should. Let's derive it first. So I'm going to leave my cartoon up there. So I'm going to say I've got some electric potential phi. And do I have that? Have I backed that up enough? Well, let me jump to this chase. I'll come back. So the Debye length is equal to K Boltzmann times the temperature divided by the density times the electric charge squared times 8 pi. And that 8 pi is for CGS. So I'm gonna show you where this comes from. So I have some electric potential phi. And how is the electric potential related to the electric field? Gradient, right? So grad phi equals E. So del squared phi equals rho free. Got it? So del squared phi, let's flesh out what rho free actually means. What does rho free mean? So there's a minus 4 pi times, let's say I put a negative charge there, times the ion density minus the electron density times the charge of the electron. Does this make sense why I'm calling this rho free? This is the difference between the ion and the electron densities. So the difference is going to give me whatever net charge is in that little region of space. So the free charge is the difference between the densities. Yeah.
Is that N at the bottom of your Debye line?
Yeah, that is the mean density.
Okay.
Sorry. Every time you look at an equation again, you get some new insight. So, pardon me, I'm having a moment with these equations. So I'll show you where this is the mean density of the gas, and I'll show you where that comes up. Actually, right now. So we're going to pause it. And I kind of hate, like, I went on a long tirade about why when you stick in that e to the ikx stuff, you're not making stuff up. There's really deep physics behind that, deep mathematics behind that. This is just making stuff up. So we're going to posit that the ion and the electron densities go like the mean density times some exponential fall off, e to the plus or minus e phi over kt. So this quantity, e to the energy over kt, and maybe this is a minus energy. Let's call it minus delta E. Have you guys seen this before?
Yeah.
Yeah, e to the energy over kt. This shows up in thermodynamics all the time.
Fermi Dirac, right?
Yeah. Well, this isn't Fermi Dirac yet. This is the Boltzmann factor.
Correct.
And what this tells you is how probable is this energy state if delta E is, yeah, so that's depends on the sign of delta E. So it's the relative energy relative to the kinetic energy, to the thermal energy. KT is the thermal energy. So we're doing something similar here. So this is my electrical energy over my thermal energy. We're just going to posit that we have some kind of exponential fall off like that. because that's a reasonable thing to do. It's the energetics, it's the probability of the energetics. So we Taylor expand this, and this gives us n naught times 1 plus or minus E phi over KT. So plus is for ions and minus is for electrons. So I've got two equations here. So I can just I can take the difference between those two equations. So I'll just say Ni minus Ne equals N naught times 2E phi over KT. So I'm just taking the difference of this equation and for the ions and minus this equation for the electrons, and the 1 cancels out, and I'm just left with that. So now I can plug that back into here, and I'm left with del squared phi equals, I got a 4 pi, I got an E squared, I get a phi, I get a KT. Is that everything? Oh, I'm missing a 2, so that's an 8 pi. 8 pi n naught E squared over KT. Yeah. So then I can just solve this, and I just get that phi equals my background potential times e to the minus, oh, I got dropped a minus sign. 8 pi E squared over KT phi, or phi equals phi naught E to the R over lambda debye. Oh, I missed an R up here, R. Where lambda debye is equal to what I said over there, KT over N naught E squared times 8 pi. So
it's over R or times R?
times R here, because this is a gradient with respect to R. So this has to be some function of R. The solution has to be some function of R. So we get something that's phi. Well, it goes like phi naught E to the R over lambda D is the solution, and there's a minus sign there. Right? Yes. Okay, I'm probably not going to ask you to rederive the Debye length, but I am going to be ask you to be familiar with using it and computing things from it. Okay. I do not have time to do the plasma frequency, but I will do the cyclotron frequency. Does anybody have any questions about this? So the basic idea is the Debye length is the self-screening length in a plasma. So I've got a bunch of charges, I've got a bunch of pluses and a bunch of minuses. If I'm looking at structures that are small, then I see a lot of electric fields. But if I'm looking at something that's big, if I zoom out, then the electric fields all wash out. So now what about time scale? Because these moving charges will make radio waves, or X-rays, or gamma rays. Yeah, I can do this fast. F equals m dVdt of v. It also equals qv cross b. Right? Now we're in CGS, so this is v over c. That c is important. This should be familiar to everybody, yeah? Holler if it's not, or I'll go through that again. Okay, so let's write out the components. Let's assume that I'm in 2 dimensions. I have a magnetic field that's coming out of the board, and I have a velocity in this direction. I just write out what this is for each of my components, and I get d by dt of vy equals q over mc times bz bx. So here, actually, bx is coming out of the board, and this is y, and this is z. So this is just the Vy component of this, and then also d by dt of Vz equals minus q over mc Vy, Vx. That make sense? So we're going to do the same stunt we've done a whole bunch of times. We're going to cross differentiate and then add the two equations together. So I differentiate this, and then I have a second derivative in y and a first derivative in Vz, so then I can plug in this derivative in Vz and stick it in there. And I'm left with d by dt of y of v, d squared by dt of y equals q Vx over mc times Vy. So then Vy is just equal to cosine of, oh sorry, this is, I got that squared, because you get two of them. It's just cosine of QB over MC times T. So this, QB over MC, is called the cyclotron frequency. I got a job for driving this when I was an undergrad. I wanted to do undergrad research with Alan, who's a high energy physicist. And I went to him and I said, I would like to do some undergrad research with you. And he said, tell me how an electron moves in a field. And so I struggled. I didn't do it very cleanly, and I really kind of half-assed it, but I got the basic idea. I was like, okay, I know that this velocity is going to go like Vz. Vz's got to go like the other one, so it has to move in a circle with this frequency. I don't think I actually got it right, but I got the physics right enough that he gave me a job, which wound up being very useful. So in a uniform field, particles go in circles. That's what this gets me. So this is cosine omega t, so this is just going to go back and forth. The z velocity does the same thing. So you just get that the electron goes in a circle with a frequency that's qb over mc. That's the cyclotron frequency. The plasma frequency, so this is just for one electron. The plasma frequency, which I'll do on Tuesday, is if I have a body of charges with some density and I move that, and I'll look at that response, which you get a similar expression, but it's a little different. It doesn't have a magnetic field in it, but it's otherwise similar. So, okay, I think I'm going to stop there. Does anybody have any questions about any of this today? Cool. So hopefully, so my plan for the rest of the semester is to do more MHD. So we're going to derive the MHD equations, and then we'll look at stability. We'll derive waves again in the MHD case, and then we'll look at some weird energetics, and hopefully we'll get to reconnection, which is why the sun is hot. And if everything goes well, we're still on track to do dynamos, or at least a little bit of dynamo. And that's how a magnetic field can get amplified by turbulent motions. So cool.
Are dynamos things we also make?
Yeah, we can make a dynamo with a waterfall and a magnet and some parts. Let's see. Okay, let's see. Nam and Jonathan didn't get their things back. So I'm gonna